welcome to the Agile Software Engineering Deep Dive. My name is Alessandro Guida, and in this episode I want to explore something that has shaped my entire engineering career. The beauty of mastering algorithms, not in the competitive programming sense, not as an academic exercise, but as a professional foundation. Over the years, I have seen many talented engineers become extremely skilled at assembling systems. Frameworks, APIs, integrations, AI tools, all used with impressive speed. And that is real progress. But I have also seen something slowly fade, the ability to reason from first principles when the abstraction breaks. In this episode, I reflect on the difference between assembling software and mastering it. I share a story from early in my career when a geometric clipping algorithm solved a very real performance problem, long before modern UI frameworks existed. We will talk about algorithmic thinking, about constraints, about complexity, and about why understanding what happens beneath the abstraction layer is still one of the most durable advantages an engineer can build. This is not nostalgia. It is not a rejection of modern tooling. It is a reminder that tools change, but ideas endure. If you are a student, an engineer early in your career, or a manager responsible for growing technical depth in your team, this episode is for you. Let's dive in.
I was looking at a meme the other day that I think just perfectly encapsulates the modern developer experience. It was this picture of a duck, gliding peacefully on a pond, looks totally serene, right? But then the camera cuts to what's going on underwater, and those little webbed feet are just paddling furiously, all tangled in weeds and old fishing line.
Ah, the classic duck paddling metaphor.
100%.
Except in our world, the weeds are probably dependency conflicts.
They're definitely dependency conflict, and the pond is a code base that nobody actually
understands. Right.
Exactly. And it gets at this central tension we are seeing in software engineering right now. We have never, ever been faster at building things. You can, NPM install a library, spin up a serverless function, connect a database, and have a product live in an afternoon. It feels like magic.
It does.
But the source material we're covering today argues that this magic, it comes with a hidden tax.
A tax that, it's getting more expensive every year. We're trading understanding for speed, and eventually that bill comes due.
We're diving into a really compelling piece of writing. It's titled The Beauty of Mastering Algorithms. And before anyone tunes out thinking we're about to, do a review of bubble sort or binary search trees for some whiteboard interview stop, that is not what this is about.
Not at all. In fact, the author specifically calls out that whole interview grind as, well, a distraction. This isn't about memorizing syntax for Google or Meta. This is more of a manifesto about the difference between being a software assembler,
someone who just glues parts together,
right, and being a true master, someone who understands the machine well enough to rebuild it when that glue melts.
Software assembler. That's a sticky term. It sounds a little bit derogatory, but the author implies it's actually the default state for most of us, isn't it? It's not something to be ashamed of. It's just where the industry pushes you.
It is. And it's not necessarily an insult. It's more of a byproduct of how good our tools have become. The author, who writes from the perspective of a mentor who's watched decades of careers rise and fall, points out a quiet shift. We have a generation of engineers who are incredibly fluent in frameworks, React, Django, Spring, but who treat the underlying logic like a total black box.
They can drive the car at 100 miles per hour, but they have no idea how the combustion engine actually works.
Precisely. And that works great, until the car breaks down in the middle of a desert. The core argument here is that knowledge of algorithms and the mathematics of computing isn't just academic trivia. It's the only reliable way to break through the seniority ceiling.
Let's dig into that ceiling, because I think a lot of people feel it. You get to a certain point where you can build features fast, but you aren't the one designing the system. The author coins a phrase that I think is going to stick with me, the assembly illusion.
It sounds like a sci-fi thriller title, doesn't it? The assembly illusion.
It really does. But break it down for us. What exactly is the illusion?
The illusion is that because you can build complex systems easily, you therefore understand complex systems. Modern development is just. It's layers upon layers of abstraction. We have code that handles memory management, concurrency, database optimization, networking, You don't have to think about any of it.
Which, to be fair, is usually considered progress. I don't want to manually allocate memory every time I write a string of text. That sounds absolutely miserable.
Oh, no, and the author agrees. This is not a back-in-my-day nostalgia trip.
Yeah.
The value of abstraction is massive. It lets us solve business problems without reinventing the wheel every single morning. The trap, the illusion, happens when that abstraction completely replaces understanding.
So it's the difference between using a tool and relying on it blindly.
Exactly. If your primary skill is just selecting the right library or API to solve a problem, your capability is strictly limited by the menu of options other people have picked for you.
You're limited by the catalog.
Right. You become a shopper, not a chef. You can assemble a meal from pre-made ingredients, and it might taste good, but what happens when you have a dietary restriction that isn't covered by the pre-made stuff? Or what happens when the pre-made sauce tastes weird and you don't know what's causing it?
That's the divergence point the text talks about, the moment where careers just split.
Yes. It usually happens around a non-standard problem. A performance bottleneck is the most common one. Let's say your app works fine with 1,000 users. Then you hit 100,000, and suddenly the server costs are exploding or the latency is unbearable. The assembler looks for a caching library to slap on top of it. They try to add another tool to fix the problem that was caused by the tool.
Is just duct tape on top of duct tape.
Meanwhile, the master opens the hood. They reason from first principles. They look at the data structures. They ask, why is this operation taking this long? Is it the network? Is it the disk? Is it the way we're traversing this list? They don't look for a patch. They look for the architectural flaw.
The source material has this incredible case study that illustrates this so perfectly. It's the window manager story. And I love this because it's so visceral. It takes us back to a time before, operating systems just handled Windows for you.
This is such a great example of constraints forcing creativity. So the author recounts building a desktop system completely from scratch. We're talking about the logic required to have overlapping, movable windows on a screen.
Which we totally take for granted now. You drag a window, it moves. You put one window over another, it covers it. It seems trivial.
Deceptively simple. So the author gets it working. With 2 or 3 windows, it looks great. It's a convincing illusion of a desktop. But as soon as they added more windows, say 10 or 20, the system just ground to a halt. It became sluggish. Dragging a window was like moving through molasses.
And this is where the assembly illusion would kill you today. Because today, you'd assume the framework was slow or the hardware was too old. You'd say, well, this machine just can't handle 20 windows.
Well,
but back then, there was no framework. It was just their code.
exactly. They couldn't blame the library. They had to diagnose it. And it turned out the system was using what's often called the painter's algorithm. Every single time a window moved, the computer would redraw the background, then the bottom window, then the next window, all the way up to the top.
Oh, that sounds incredibly inefficient. It's like if I wanted to move a sticky note on a whiteboard, but to do it, I had to erase the whole board and rewrite everything else first just to place the sticky note 1 inch to the left.
That is a perfect analogy. And worse, it was repainting pixels that hadn't even changed. It was just burning processing power doing redundant work. Now, here's the pivot point. An assembler mindset might say, we need a faster processor, or we need to limit the number of windows.
Right. Sorry, users, you only get 3 windows. It's a feature, not a bug. It's minimalist mode.
Right. But the author went to the library, not the code library, the actual book library.
Right. They went back to math, specifically geometry and set theory. They realized this wasn't a coding problem at its heart. It was a logic problem. They needed a way to calculate only the exposed regions of the screen.
Rectangular arithmetic.
That sounds intense.
It's actually quite beautiful when you think about it. If window A covers half of window B, and I move window A, I only need to redraw that specific sliver of window B that just got revealed. I don't need to touch the background. I don't need to touch window C over in the corner.
So they wrote an algorithm to calculate the intersection of rectangles.
And the result was drastic. The system became lightning fast, not because they found a faster draw command, but because they stopped asking the computer to do stupid work.
There is a quote in the text about this that I highlighted. Since the solution was an algorithm rather than a framework feature, it was portable.
That's the key takeaway. They wrote this in C, which was just the language of the time. But the idea, the logic of calculating intersections is language agnostic. You could write it in Python, in Rust, in JavaScript. If you master frameworks, you master a tool that will be obsolete in 5 years. If you master algorithms, you master ideas that last forever.
Ideas that outlive the technology. That is powerful. But I want to pause here and play the skeptic for a minute.
Please do.
Because when I hear math and algorithms, I don't feel empowered. I feel anxiety. A lot of listeners hear this and think, okay, do I need to go back to college? Do I need to be able to derive big O notation on a napkin?
It's the post-traumatic interview syndrome. We've all been there.
Right. So does the author expect us to be able to handwrite a merge sort from memory? Is that the goal?
No, and they are very, very explicit about that. The author says, mastering algorithms is not about memorizing sorting complexities or solving competitive programming puzzles. That's a sport, not engineering.
Okay, good. So if it's not memorization, what is the definition of algorithmic thinking here?
It's defined as learning to think under constraints. It's a mental model for resource management.
Unpack that. What does thinking under constraints look like on a Tuesday afternoon when I'm just trying to ship a feature?
It means you stop looking only at the happy path. The happy path is where everything goes right. The user enters valid data, the network is fast, the memory is empty. Assemblers build for the happy path because it's the easiest thing to code. Algorithmic thinkers build for the worst case.
They assume the house is going to catch fire.
They assume the dataset will grow by 100x. They ask, what happens to this loop if the list has 1,000,000 items instead of 10? This is where we touch on that log-R versus log-N concept mentioned in the text.
Let's clarify that for the listeners who might be a little rusty on the math shorthand. I know I always get these mixed up.
Sure. Think of it like a networking event. Imagine you're at a party with 100 people. If you want to find a specific person, say Bob, you could go up to every single person and ask, are you Bob?
Okay, it takes a while, but I'll find him eventually.
Right. That's linear time, or $9. The time it takes is directly related to the number of people. If there are twice as many people, it takes twice as long. Simple.
Okay, makes sense.
Now imagine you have to introduce everyone to everyone else. You have to take person A, introduce them to B, C, D, then take person B, introduce them to C, D. That's a double 2D. The work grows exponentially. With 100 people, it's manageable. With 10,000 people, you will die of old age before you finish.
And in code, that death by old age is your server hanging and the user just closing the browser in frustration.
Exactly. An algorithmic thinker looks at that introduction logic and immediately says, this won't scale. How can we structure this differently? They optimize the logic, not just the code speed.
Yeah.
And this ripples out to everything. Database schema design, API structure, everything.
It seems like it's really about discipline. It's about not accepting the first solution that works, but finding the solution that lasts.
Correct. It's about defining your invariants, the things that must always be true no matter what the user does. It prevents the system from getting into a corrupted state where the database says one thing and the UI says another. It's about predictability.
Now, we have to address the elephant in the room. We are recording this in the era of AI.
We can't avoid it.
The argument I hear constantly, and frankly I've used it, is why do I need to know how to write a complex sort or a graph traversal? I could just ask ChatGPT or Copilot, and it spits out the code in 10 seconds.
It's a valid question, and the author doesn't dismiss AI. They call these tools extraordinary accelerators.
They are. I use them every day. They save so much typing.
But here's the nuance. AI is a probability engine. It's trained on existing code. It is fantastic at solving common problems with common solutions. If you need standard boilerplate for a login screen, AI is unbeatable.
But we don't get paid the big bucks for the standard boilerplate.
Exactly. The assembler uses AI to write code they don't understand. The master uses AI to generate drafts that they then critique. The trap is that AI can be subtly wrong.
Subtly wrong is the stuff of nightmares. I'd much rather it be completely broken.
Me too. If it crashes, you know it's wrong. But AI might give you a solution that works functionally but has a hidden memory leak. Or it uses a library that is technically deprecated. Or, and this is really common, it solves the problem in that docked brute force way we just talked about, because that's the most common example it found on the internet.
Because the internet is full of bad code examples.
Exactly. The AI is scraping Stack Overflow where people post the quick fix, not necessarily the scalable fix. So if you don't know the fundamentals, you can't spot the flaw. You're just accepting the machine's homework.
You're blindly trusting a junior engineer who's read every book in the library but understands none of them.
That's a great way to put it. The author puts it this way. The real distinction is not whether you can produce code, but whether you can design a solution from first principles when the default answer does not hold.
That connects right back to the career aspect. I think a lot of people feel stuck at that senior developer level. They can execute tickets fast, but they aren't getting invited to the architecture meetings. They aren't the ones making the big decisions.
That is exactly the ceiling we discussed. Strategic influence, the ability to steer the ship rather than just row it, comes from depth. The engineers who shape the architecture are the ones who can look at a proposed feature and say, that data structure is going to deadlock us in 6 months, or we can simplify this entire microservice mesh into a single efficient process if we just change how we store the state.
They become authorities because they can see the matrix, basically. They see the consequences before the code is even written.
They can see the cost of complexity. Assemblers add complexity, masters subtract it.
I love that. Assemblers add complexity, masters subtract it. That should be on a t-shirt. So if I'm listening to this and I'm realizing, I might be an assembler, or maybe my team is full of assemblers, what is the move? Because the author has some advice for managers, right?
Yes, and it's actually quite counterintuitive for a lot of modern tech cultures. The advice is stop prioritizing speed over everything else.
Easier said than done when the roadmap is on fire.
True. But if you want a team that can solve hard problems, you have to make space for growth. The author suggests treating study as work.
Meaning, I could read a textbook on company time.
Yes. If algorithmic competence is required for the job, then acquiring it is the job. It shouldn't be something you have to do at 9 p.m. after the kids are asleep.
That's a huge culture shift. Most places are like, if you aren't typing, you aren't working.
It is. But high-performing engineering cultures, places like Google or Stripe, often have this built in. They also suggest changing how you do code reviews in meetings. Don't just check for syntax errors. Create internal forums to discuss concepts. Ask questions like, why did we choose this data structure? Or where are we carrying unnecessary complexity? Make the why as important as the what.
It elevates the conversation from, does this compile, to, is this wise?
Precise.
And for the individual learner, the author provides a reading list. And I have to be honest, looking at this list, it's intimidating.
It is the heavy hitter list, for sure.
I mean, Donald Knuth's The Art of Computer Programming. That series is famous for being on everyone's shelf and in nobody's brain. It's like the infinite jest of computer science.
It's the Bible of the field, but it is incredibly dense. And the author acknowledges that. You don't start with Knuth unless you're a masochist or a genius.
Or both.
Or both. But they list accessible entry points, too. Grokking Algorithms by Aditya Bhargava is fantastic.
I've seen that one. It looks almost like a comic book, right? With the pictures.
It uses illustrations, yes. It's very visual. It breaks down things like graph search or dynamic programming using cartoons and simple analogies. It's very friendly.
Then there is the Algorithm Design Manual by Steven Scienna.
That one strikes a great balance. It focuses on the war stories, real-world examples of where these things matter. It's less about the mathematical proof and more about, here is a problem I faced in the industry, and here is the algorithm that solved it.
And Tim Roughgarden's Algorithms Illuminated.
Another excellent series. Very clear. Breaks things down into manageable chunks.
So the goal isn't to become a walking encyclopedia.
No. The goal is resistance training for your brain. Even if you never implement a red-black tree in production, and you almost certainly won't, the effort of understanding how it works changes how you approach other problems. It builds that mental muscle of thinking under constraints.
It's like how a football player lifts weights. They aren't going to bench press anyone during the game, but the strength helps them block.
Exactly. It gives you the stamina to handle complexity.
We're coming to the end of our time, but I want to circle back to that window manager story one last time. It really sticks with me because it feels like a lost art.
It is, in a way, but the author argues it's a recoverable art, and they leave us with a final litmus test to gauge your own engineering maturity.
What is the test?
When the abstraction breaks, can you continue reasoning from first principles?
That's the heavy hitter.
When the library fails, when the documentation is wrong, when the server is on fire and the error logs make no sense, do you panic and start guessing? Do you start randomly changing config values hoping one of them works?
Or can you dig down into the bedrock and figure out the logic?
If the answer is yes, you are practicing engineering in its fuller sense. You aren't just a user of the technology, you are a master of it.
Frameworks are shared code. Algorithms are shared ideas. That line stuck with me.
And ideas outlive technologies. Frameworks come and go every few years. The Reacts, the Vues, the jQueries, they fade. But the logic of how to efficiently search a database, how to manage concurrent users, that isn't going anywhere.
So here is a provocative thought for you to mull over as you go about your day. Think about the last piece of software or code you really struggled with. Maybe it was buggy, maybe it was slow, maybe it just felt hacky.
Ask yourself, was the problem that you didn't know the library well enough? Or was it that you were trying to solve a structural algorithmic problem with a tool meant for assembly?
Were you trying to paint the window from the bottom up?
Exactly.
That's the question to chew on. Thanks for diving deep with us today.
Always a pleasure.
We'll catch you on the next one.
Thank you for listening to the Agile Engineering Deep Dive podcast. If you found this episode valuable, feel free to share it with someone who might benefit, a colleague, your team, or your network. You can access all episodes by subscribing to the podcast and find their written counterparts in the Agile Software Engineering newsletter on LinkedIn. And if you have thoughts, ideas, or stories from your own engineering journey, I'd love to hear from you. Your input helps shape what we explore next. Thanks again for tuning in, and see you in the next episode.